Vamos a hacer hoy es, es hacer este cursito. ¿Por qué? ¿Por qué? Ahí. Pero pues les tengo que dejar ver pantalla, ¿no? ¿Qué es esa pantalla? No se va a tampoco, tampoco. Esta. Vamos a ver si podemos hacer este curso. Claro, ¿no? Comenzar en 7 semanas. Debería dedicarse entre 5 y 7 horas. ¿Qué? 5 y 7 horas. Plan de estudio. Producción electrónica. Métodos del circuito resistivo, análisis de nodos. Mire, detesto el curso, los cursos en línea. ¿Vale? Plagio. Son suyos. Comience que plan de estudio, recursos, visión general, repaso de los elementos del circuito. Ujú. Todo esto hay que repasar, mira. El primer orden, ok.
Botrick se ha unido correctamente.
Opción de transferencia, segundo orden. Activo. Yo lo que no sé es esto. Esto es en inglés. Semana uno todavía. Pues que esto ya lo sé. Digamos, semana 2, semana 3, semana 5, semana 6. Falta la 4, ¿no? Semana 4. Me falta la 6. No, no, ya está. Falta la 7. ¿Qué es esto? ¿Qué es esto? Wikipedia. ¿En serio? ¿En serio Wikipedia? Open. Open, mira. Tengo que hacer una carpeta para todo esto. Y siguiente. Navegador, formación profesional. tecnología y geometría ofrece cursos cortos, formato de reflexión. ¿Qué más? A LinkedIn. Mm, ok, te doy la bienvenida. A ver cómo completa. Siguiente.
Welcome to Introduction to Electronics. I'm Dr. Robinson. In this
Monólogo. Está despierto. Bueno, vamos a ver clase entonces. Vamos a ver. Es que había un curso para hoy.
lesson, I wanted to give you a quick overview of things to come in this course. Now, there's really no need for me to motivate electronics to you. You couldn't be watching this video without electronics and electronic devices, and you wouldn't have available to you all of the technology that you use.
No tendría a su disposición toda la tecnología que usan a diario. me puede cambiar durísimo. Amo este
every
video.
day. Now, the particular devices that we are going to study in this course are the diode, the transistor, and the operational amplifier. The diode and transistor can truly be considered to be fundamental electronic devices, while the op amp is a more complicated device that is composed of the more fundamental devices. Now, as we proceed through the course, we will study
No, pero eso habla de re rápido. Bienvenido a la introducción electrónica. Soy el doctor Robinson de esta lección. Le quiero dar un breve resumen. ¿Qué? Sam no está viendo este video sin electrónica, un dispositivo eléctrico. A su disposición toda la tecnología que usan a diario. Escuchémoslo en inglés.
the operation of these electronic devices, and we will also study particular application circuits which use these devices to achieve some functionality. And you can consider these application circuits to be building blocks, which can be combined together to form more complicated circuits. Now we begin this course with a review of topics from linear circuits. We then move to a module on operational amplifiers, followed by one on diodes, and we conclude with a module on transistors. Now, at the end of this course, you should understand the operation of these fundamental devices, and you will have available to you techniques that you can use to analyze more complicated circuits. And overall, this course will give you a good foundation for the further study of electronics. So, thank you for taking this course. I hope you enjoy it, and I will see you in future lessons.
Eso fue toda la introducción. Sigamos.
Welcome to the Introduction to Electronics. I'm Dr. Ferry, and this lesson will be a review
Soy la doctora, dice la doctora Perry. Un
of
repaso,
circuit
dice.
elements. And actually, the next few lessons will be a review of basic circuit type principles that you're expected to know before you come into an electronics class. They cover linear circuit principles. So if you want to review these lessons, you're welcome to do it. If you want to skip them because you're very familiar with circuit elements, linear circuit elements, then you're free to do that as well. In this lesson, we will review resistors, capacitors, and
Dice esta selección, repasaremos la resistencia de los condensadores y los inductores.
inductors and their current voltage
Conductors.
characteristics, as well as looking at sources and nodes.
¿Yo será que puedo esconder esto? Sí lo puedo hacer. Ya. Sí, sí. Mm, y que entra hartísima gente hasta ahora. Bárbaro. Qué video tan largo, ¿no? Ya los voy a poner a estudiar. Le puedo poner aquí para que vean, para que vean y aprendan. Ahí, ahí alcanzan a leer, ¿no? Ahí.
Nodes. So let's look at these passive elements, a resistor, a capacitor, and an inductor. In each of these cases, we show by convention that the current is going into the positive side
Ahí dice que la voltaje es igual a la corriente por resistencia.
of the voltage. And with that sort of convention, we get the equation. So this
Primero, GPT. Busquen sus matrix. GPT, cállate la boca. ¿Vos quién sos? Mm, ahí cambiaron el. Vos sos Andrés, ¿no? Ya lo subí el informe. El artista. El artista. El artista. Ahí esa foto de proxeneta que no, esa foto no, no sé. ¿Quién sos, ve? Habla claro. Vos Andrés, ¿no? Y volver a amigos para cuando. Está en pasto eso levanta. En pasto.
equation corresponds to this convention where this arrow is flowing into the positive side. And this particular equation is called Ohm's law. The voltage is equal to current times the resistance. The resistance is measured in ohms.
Eso está bueno.
And the symbol is an omega. Now, if I go on to a capacitor is an energy storing device. And it is governed by this differential relationship between the current through the capacitor and the voltage across it. And note again that the convention,
En pasto se levanta.
which we represent as H. And it's oftentimes will
Jonathan.
look at 10 to the minus 3 or millihenries. So the range that we often look at is, again, millihenries. And notice again that by convention that the current is going into the positive side of the voltage in order to get this equation. These are called passive elements because they don't require a power supply just for that element. There are other elements that we will see in electronics that we'll call active elements that require a power supply to make them work, to make them give their characteristics. Now let's look at the basic series and parallel connections of resistors, inductors, and capacitors. The series resistors, you just sum them up. So the total resistance from this point here to this point here is the sum of the two things. And inductors work the same way. The total inductance between this point and this point is the sum of the two individual inductances. And again, this would be in ohms and inductors would be in henries. Now the parallel connection's a little bit different. Parallel connections meaning that the resistors are connected together at one end and again at the other end. Whereas in series, they're connected only between them. The resistance, total resistance between this and this, so it's equivalent resistance across everything, is the inverse of the sum of the inverses. Now if I only have two resistors, I can simplify this. So if R3 is equal to 0, and I only have R1 in parallel with R2, so that represents the fact that R3 is equal to 0, and I've only got two resistors in parallel, then that would be equal to R1 times R2 over R1 plus R2. And we can get that by setting R3 to equal to 0 here, or dropping that off of here, and then just simplifying this form. So then we've got the same relationship for inductors in parallel, this relationship here. And so we would also say L1 in parallel with L2, be L1 times L2 over L1 plus L2. Now capacitors are a little bit different. They operate in a different way. The series capacitors has the same equation that we used before when we were looking at parallel resistors and parallel inductors. So capacitors in series, you use this relationship. Capacitors in parallel are easier. The equivalent capacitance between this point and this point is just the sum of the individual capacitances. So connections and sources. When we look at a schematic, we'll see a ground. It's very commonly used, and the ground looks like this.
¿Y qué está diciendo? Tierra, nodos, voltajes.
It's a reference for 0 volts. When we look at linear circuits with DC voltages, maybe batteries supplying it, we oftentimes pick a ground and say that's our reference node. And reference node meaning that
Corrientes.
we're going to say the voltage with respect to anything else, any other point in that circuit, is the potential with respect to that ground node. And so it's just a reference node. Now when we get to electronic circuits, it usually has a little bit more meaning to it because we oftentimes power these electronic circuits with AC or wall power. You know, you plug it into the wall. And when you plug it into the wall, we're connecting to a power system. And that power system, the power that comes into your house, usually is grounded, meaning that there's a connection down to the ground, to the real ground, to earth. And so when the power supplies are connected to the wall, and then they're connected to your circuit, oftentimes we're required to ground our circuit. So in that case, the ground oftentimes has a more physical meaning to it, really relating to the ground, the true ground. A node is anything that has the same potential, that's connected electrically together. So every point on here is the same node. Now I might have different current going through these branches leaving this node, but the voltage everywhere on this node is the same with respect to ground. Our voltage source, we have independent sources for both the voltage source and the current sources. Independent sources will show as circles, the units on a voltage source are going to be in volts. Units on a current source are going to be in amps. Oftentimes, we supply them with smaller amps, maybe milliamps. Dependent sources have the little diamond shaped. Now, the difference between an independent source and a dependent source is that the independent source doesn't depend on the rest of the circuit. It's going to be independent. No matter what you do with the rest of the circuit, you define a function for that independent source. Now, dependent source, there's a dependence on some other part of it. For example, I might have this voltage supply, gives me a voltage, but it might be dependent on current in one of my branches. Or I might have a dependent current source, which might be dependent on a current in one of my branches, might be dependent on a voltage at one of my nodes. So these two are dependent on something else that's happening in the circuit. This right here is independent of what's going on in the circuit. Now, all voltage sources have the units of volts, and all current sources have the unit of amps. Let's look at a common connection here. This is a circuit schematic. We've got an independent voltage source, an independent current source. We've got our ground right here. We've got our resistors. In this case, we don't have any capacitors or inductors. We've got some nodes here. These are all connected together. That's one node. That's another node. Here's a node right here. And then we've got some nodes that only connect two resistors. So this resistor, this is a series combination because they're connected right in the middle. I don't see any other obvious connections. These two are not.
Oh.
Welcome to the Introduction to Electronics. I'm Dr. Ferry, and this lesson will be a review of circuit elements. And actually, the next few lessons will be a review of basic circuit type principles that you're expected to know before you come into an electronics class. They cover linear circuit principles. So if you want to review these lessons, you're welcome to do it. If you want to skip them because you're very familiar with circuit elements, linear circuit elements, then you're free to do that as well. In this lesson, we will review resistors, capacitors, and inductors and their current voltage characteristics, as well as looking at sources and nodes. Welcome back to electronics. This is Dr. Ferry. This particular lesson is a review of Kirchhoff's laws. In a previous lesson, we reviewed linear circuit components such as resistors and capacitors and inductors. In this one, we're going to go through more detail of Kirchhoff's current law, or KCL, Kirchhoff's voltage law, or KVL. Kirchhoff's voltage law states that the sum of voltages around any closed loop is zero. Now, we show an example of a closed loop here. And in order to apply this, we would have to know what these voltages. So suppose this is V sub D, V sub A, V sub G, and these are all measured in volts, and this is V sub H. So I want to do a sum up the voltages around here. Now, if I'm sum the voltage from this point to this point, so I'm looking at the voltage potential, I actually gain voltage from this point to this point. But when I do a voltage, Kirchhoff's voltage law, I want to make sure that I'm always consistent with the way I use the polarities. So I use a little trick in doing this. I use the trick and say, if I'm going to be summing in this direction, if I come to a plus sign first, I add it. If I come to a plus sign here first, I add it. In all these cases, I come to a plus sign first if I go around in this direction. So I'm going to add these all. If I were to come to a minus sign first, I would subtract. That's just my trick in making sure I get the polarity right. So starting at this point, I would have V sub H plus V sub D plus V sub A plus V sub G all have to sum to zero. And that's going to be true of any loop. It'd be true of this loop, it'd be true of this loop, any closed loop. Now I'm going to have you do a KVL quiz here. So looking at this circuit, I want you to find VH. Now coming back to the solution here. Find VH, I want to do a KVL. Well, I can do a KVL around this loop, but I don't know what this voltage drop is. So let me do a KVL around this loop right here. And the way I do a KVL is in the direction I go, if I hit a plus sign first, I add it. If I hit a minus sign here, as in this case, I would subtract it. Now, it's not strictly physical because actually I'm losing potential as I go from here to here. But it's just a trick that I use to keep my polarities correct. So going around here, starting with plus VH, and then I get to the minus 2. Over here, I get a plus, minus 1, and then around here, I get a minus 5, and then plus 4 equals 0. So when I add these up, let's see, I'm going to have a minus 8 plus 4. In other words, solving for it, I get a 4 volts. Now let's look at KVL in parallel circuits. So I've got these two elements that are parallel to one another, and that's the only thing in this circuit. So if I do a KVL around here, and this is V sub A, and this is V sub B, going around here, I would have, in this direction, V sub A minus V sub B, because I hit that minus sign first, is equal to 0. In other words, V sub A is equal to V sub B. And that is true anytime we've got two elements that are in parallel with one another. They're going to have the same voltage drop as long as you've defined them with the same polarity. So any two elements that are in parallel with one another have the same voltage across them. Now this is a numerical example, an actual circuit example with resistors in there of a KVL. And I'd like to be able to solve this and do, for example, a Kirchhoff's voltage law across this. So let me write this. There's lots of loops I could do. And do this loop right here. I can do this loop up here. So let me write a Kirchhoff's voltage law around here. So I would like to be able to write, so I'm going to do it around here. I'll need to be able to mention or write an expression for the voltage drop across this resistor. Now by the convention, we show that resistance goes into the plus side in order for us to be able to use Ohm's law. So we'll call that V sub 1. So if I want to go around here, I hit the minus sign first, minus 10, plus this voltage drop here, V sub 1, plus V0, and that's all I've got on this loop is equal to 0. So V sub 1 is equal to I sub 1 times 20. V sub 0 is equal to I sub 2 times 10. And this is by Ohm's law. So now I've got an expression that I can use to solve for these variables here in terms of the currents. I can also do a loop around this way. Suppose I do this loop around here. So in this case, I hit the plus sign first. So it's plus 2 minus V0, because I hit that minus sign, and then plus this voltage drop. Well, remember the current goes into the plus side, plus I3, 5 is equal to 0. So I have another expression, and V0 again is equal to I2 times 10. So what we've been showing here is how to write KVLs for a particular circuit, an actual circuit, that we're making use of Ohm's law for that. Kirchhoff's current law says that the current entering a node equals the current leaving a node. For example, suppose I've got this current. This is a node right here, and this is a node because everything here is connected. So this is a node there, and call this I sub A, and this I'll call I sub B, I sub E, and I sub d. So if I do KCL at this node, I would sum up everything entering, and that would be I sub b plus I sub d is equal to the sum of what's leaving, I sub a plus I sub e. And that's true for any node. So I've got a node over here, and a node over here, and a node over here. It's true at every node. So in this particular case, we look at, for example, if we draw the current, if I've changed the directions. So now this one, I'm showing this way, this way, this way. Now what's entering is I sub a plus I sub b. What's leaving is I sub d plus I sub e. So if I change the arrow, the reference of my current, I have to just be careful that I'm consistent with it. Now, if I have two elements in series with one another, then all the current, this is a node between them, the current entering has to equal the current leaving. So if this is I sub A and this is I sub B, then the current that enters this node, I sub A, has to equal the current that leaves this node. So that means that any current that flows through elements that are in series with one another is the same current. So this current is all the same because they're in series. Let's look at a KCL for a particular numerical example, a circuit, real circuit. And I'm going to look at this node right here. And I want to look at all the currents entering and leaving. And let me define this as being the one that maybe I'm trying to solve for, I. So let me look at the currents entering. We have I1 is equal to I3 plus I2 plus I. And that's just how to do the KCL at this node. In summary, we've introduced the Kirchhoff's voltage law and Kirchhoff's current law. We've applied the Kirchhoff's voltage law to parallel elements and found that two elements that are in parallel have the same voltage across them. We've applied the KCL to series elements and saw that any two elements that were in series had the same current going through them. And then we also solved a simple circuit using Kirchhoff's laws. In our next lesson, we'll do a review of impedance methods. Welcome back to electronics. This is Dr. Ferry. This lesson will be a review of impedance. In the previous lesson, we did a review of Kirchhoff's laws. In this lesson, we will look at impedances. In particular, impedance is a method that we use for steady-state sinusoidal inputs. In other words, what we call AC, or alternating current inputs. So we're going to define the impedance for our basic elements, an R, a C, and an L. With a resistor, if I look at the voltage current behavior, so say this is my voltage across the resistor, and then my current is going in this way, then if I have a sinusoidal input or sinusoidal voltage across this resistor, my current's going to be sinusoidal. And in particular, it's in phase. The zero crossings are at the same time. The peak happens at the same time. We often say that doesn't matter what frequency the input is, so we can say that this is frequency invariant, that the output is, or the current is always in phase with the voltage. Now there's a couple of things that we're going to be needing here, so I want to define them. One here is the period. That's how long it takes to repeat itself. And we define the frequency as being in hertz, being cycles per second, a cycle being one time that it repeats itself. That is 1 over t, which we're going to define as f. My variable f, as in hertz, is the frequency. There's also a frequency variable in radians per second. So it's a different unit. and it is defined as 2 pi f, or in terms of t, it's 2 pi over t radians per second. And we use the symbol omega to represent frequency in radians per second. And I need all that once I go to my other variables, my C impedance and my L impedance, or I'll call it Z sub C, and I'm going to define it this way. That is 1 over j omega, omega being the frequency in radians per second, j being my symbol for the square root of -1, and then C is the capacitance. So if I define my voltage this way and my current going in this way, I can represent for sinusoidal voltage, my steady state current looks like this. Notice that the current, this being the current I and the voltage V, the current leads the voltage. Leads means it comes before. So it comes before this. So that's my impedance for a capacitor. For an inductor, it's J times omega times L. And again, if I plot the voltage-current relationship for a sinusoidal voltage, if this is a voltage in this plot and the current is in this plot, then what we say is that the current lags the voltage. It comes after it. It looks like it's delayed. So these are the 3 impedances that I'm going to need a great
Conclusión, el voltaje en el capacitor se adelanta y la corriente se retrasa, en el inductor es el inverso. La corriente se adelanta y el voltaje se retrasa.
great deal when I
Y ya, capacitor 1 sobre WC, la inductancia W por L.
analyzing circuits with an alternating current, or in other words, sinusoidal input. Let's look at impedances in series. Here's the good thing about impedances. They're messy because they involve complex numbers, but they use all the same rules that we've already defined for resistors. So impedances in series, I treat just like they were resistors in series. So this circuit is equivalent to a circuit with one impedance and that impedance is equal to the sum of the other ones, Z1 plus Z2 plus Z3. So impedances in series, they just add. So it could be 3, it could be a lot more than 3. It's just a summation of all the impedances in the series.
Todas las impedancias se convierten en nuestra impedancia equivalente.
Our equivalent impedance. Impedances in parallel. Well, I treat them just like resistors in parallel, which I get by inverting 1 over each one of them. And it's usually easier to think of it in terms of if I have 2 resistors in parallel. In other words, if this resistance isn't there, if it's if I only have these 2 impedances, so I'm going to write Z1 in parallel with Z2. If I look at this expression and Z3 is gone, then all I've got is 2 terms. I can simplify it to Z1 times Z2 over Z1 plus Z2. So that's 2 impedances in parallel with one another. Kirchhoff's laws still work. Kirchhoff's current law says that all the currents going into a node have to equal all the currents leaving the node. So the currents going in, I1, is equal to the currents leaving, I1 plus I2 plus I3. And in terms of Kirchhoff's voltage law, I can look at going around the loop this way and sum up all my voltages. And in my case, when I sum up voltages around a loop, I use a trick, and I just say, in order to get my polarity right, whenever I hit a minus sign first, I subtract that, minus Vs, and going around I hit a plus sign this way, plus V1. Going around this way I hit a plus sign, plus V2. Going around this way I hit a plus next, so plus V3 is equal to 0. In other words, I can rewrite it down this way right here. So Kirchhoff's laws still work. The only thing different about all these laws is now we're working with complex numbers. So again, impedances treat just as if they were resistors. The only thing is they're going to be complex numbers. Let's look at an example of this, how to analyze a circuit with impedances. The first thing I'm going to do is replace this circuit with impedances, Z sub R and Z sub C representing the capacitance. I've got my input voltage and my output voltage. I'm going to use the voltage divider law here. The voltage divider law says that V out is equal to Z sub C of ZR plus Z sub C times the input. Well, if I plug in for Z sub C, I get 1 over J omega C. If I plug in for Z sub R, I get R plus 1 over J omega C times VI. If I clear my fractions, I will get 1 over RC J omega plus 1 times VI, and that gives me V out. So once I know what VI is, then I can solve for V out. Now let's take a look at a series RLC circuit. First thing I do is redraw the circuit in terms of its impedances. So I've got a Z sub R in series with a Z sub L in series with the Z sub C. And I'm looking for V out, or V sub 0, in terms of V sub I. I can use a voltage divider law again. V out is equal to Z sub C over ZR plus ZL plus ZC times VI. If I substitute in, for Z sub C, I substitute in 1 over J omega C. R is for Z sub R, and J omega L for Z sub L, and then I've got my other Z sub C. If I clear my fraction here, I'm going to get a 1 in the numerator, RC J omega plus J omega squared LC plus 1 in the denominator times VI. And remember that J is the square root of minus 1, so J. And the other thing about this, it's implicit in here that I know what omega is. Omega is the input voltage. So if we say VI is equal to AI cosine of omega t, that omega is the input frequency. Maybe 100 hertz, or in which case that would be 2 pi times 100 radians per second. It could be whatever frequency we want, but it is a particular frequency to be able to solve for a particular value of V out. So in summary, we've introduced the KVL and KCL, apply the KVL to parallel elements and series elements, and we solve simple circuits using Kirchhoff's laws. All of this is applied to circuits with impedances. The bottom line is an impedance acts like a complex resistance. All of our standard laws apply. The only thing is it's messier because it's complex numbers.